Good afternoon, ladies and gentlemen, and welcome to this Smarty webinar. My name is Bob Willis, and this webinar is presented on behalf of Smart Group. The webinar we're going to hear this afternoon covers an update on the uBGA project, which is an EU-funded project under FP7. Before we proceed, I'd just like to explain some details about the webinar for you this afternoon. First of all, I would like to explain the control panel that you have on your screen. Now, the control panel allows you to close or open the panel by clicking on the orange button. You can go full screen with the webinar display by clicking on the blue button. If you want to raise your hand to ask a question during the question and answer session, all you need to do is click on the raise hand tool. Now, this will be used during the question and answer session at the end of this session. If you would like to ask a question or pose a question during the webinar, you can type the question into control box. Now, these questions will be handled at the end of the webinar, but sometimes it's easier to type the question in during the webinar and then get a response at the end of the session. If you have any technical problems during the webinar, use one of the telephone numbers provided on your registration and reminder emails. You will also need your webinar ID number and access code, which was also included on the emails provided. It's not possible for the presenter to assist you during this live presentation. At the end of the presentation, we have 6 survey questions on the event. Please take a moment of your time to complete the survey, providing any comments you would like to give. A copy of the presentation material and slides will be emailed to you shortly after completion of the survey. I'd like to thank you once again for attending this Smarty webinar session. Before we proceed, I would just like to mention a couple of other items. First of all, Smart Group has the pleasure of working on 4 EU-funded projects at this moment in time. One of these is Chip Check, which looks at methods of identifying counterfeit components. Ship Inspector, which is looking at methods of checking ships' hulls during operation and not in dry dock. And TestPep, which is involved with the welding and inspection of plastic pipes. uBGA is the project we'll be discussing during this webinar this afternoon. If you want any more information or details on any of our EU-funded projects, then all you need to do is go to the Smart Group website, which is www.smartgroup.org. On the website, you'll also find a complete diary of Smart Group's activities. Again, if you need any further information, you can email Smart Group, or alternatively click on one of the events for further information. I now have the pleasure of introducing 2 speakers who are the coordinating group for the uBGA project from Kingston Computer Consultancy. And I'd like to now introduce SP, as I refer to him, and also Ravin, who is supporting this project. Now I'd like to hand over to our 2 presenters this afternoon.
Thank you very much, Bob. I'll make my screen visible. So thank you very much, Bob, and thanks to the Smart Groups for this opportunity to discuss the uBGA project with with your members and the wider audience. As Bob mentioned, the uBGA project is an EU-funded research project that is looking at providing research that can be disseminated to European small to medium-sized associations and to large enterprises to increase the competitiveness of European production in the electronics and microelectronics industries. What I'd like to cover in this webinar is an overview of the project briefly. I'd like to talk about the industry survey that we conducted in conjunction with the member associations to determine what the current and the future requirements are for BGA and micro-BGA requirements. I'd like to go into some specific details in terms of the solder alloy requirements that the industry survey produced, the micro-BGA overall requirements, and talk about the current solder sphere manufacture, the technology as it is today and it has been through the last 10 to 15 years. After looking at the existing processes, I'd like to deal with some of the issues that we're facing in this area, and then move to the future industry benefits where hopefully we can have some input from the members of the audience. A quick overview, and I think a lot of you will probably know what a BGA is, but just to make sure we're all roughly on the same page and why we're doing this research. The BGA descended from the pin grid array. The pins in the pin grid array, the PGA packages, conducted electrical signals from an IC, from an integrated circuit to a PC board. To the PC board on which it was placed. In BGA, ball grid array, the pins are replaced by balls of solder attached to the bottom of the package. The solder spheres are held in place with tachyflux until soldering occurs, when they're reflowed to form intermetallic bonds between the package and the substrate. The package is placed onto a PCB that has pads that match the solder sphere diameters, and it's reflowed to cause the balls to melt, where the balls will then cool and solidify, forming an intermetallic bond, attaching the package very securely and consistently to the underlying PC board. The research that we're doing in the micro-BGA project is to look into BGA manufacture and to miniaturize the BGAs into micro BGAs. This will then allow the miniaturization of the IC packages and the PCB boards as the dimensions of the connectors, the BGAs, decreases. Here's a quick diagram of the setup of a package being connected by solder balls. This is to be connected to the underlying PCB. The package will be lowered onto the PCB. The solder balls attached by tachyflux will be held in place. The entire assembly will be reflowed by heating. You can see here that the solder balls will undergo some compression. Currently, a typical size for a solder ball within a BGA would be about half a millimetre, 400 microns. That will decrease to about 350 microns after reflowing. The current status of BGAs and micro BGAs is one of the concerns which led to the funding of the micro BGA project. Currently, most BGAs are produced in China, Japan, or the US. Even the European producers are subsidiaries of the US or Chinese organizations, and the dependency on non-European supply chains is a significant concern to the European Union. The Micro BGA project aims to provide the technology of BGA manufacture to European organizations through the research into the production techniques and techniques to miniaturize BGA, and this research becomes the belonging of the SMEAGs, who will then be disseminating these results to their European member associations. So organisations such as Smart Group will be the beneficiaries of the research that the project produces, and that will be then disseminated out to their member associations. In the next slide, I'd like to look at the current status of the ball grid array associations and industry, and what we're hoping to achieve in the Micro BGA project. Currently, you can see that the general size of BGA is around 200 microns. What we're aiming to produce in the Micro BGA project is a dependable way of producing sub 100 micron solder balls which can be used in BGAs. In terms of the reliability of the yield, the process capability index measured as a CPK, currently most producers or most consumers of BGAs are requiring 0.66 to 0.9 CPK, which equates to about 2 or 3 standard deviations. We're aiming at a CPK of 1.33, which relates to 4 sigma deviations around the average, so that almost all balls fall within 4 sigma deviations of the tolerance, which means 99.4% of the solder balls are produced defect-free, which in terms of a rejection rate equates to 64 in every million. While we are looking at decreasing the size of the BGAs and the micro solder balls that are being produced, we want to maintain the current throughput of about 500 million balls per day, so that that we have no reduction in throughput. And as an innovative element of the project, we're also looking at integrating these 100 micron or sub 100 micron balls into placements directly as they're being manufactured onto a PC board. The project was originally conceived probably maybe more than 2 years ago, and was proposed to the EC as it was named in those days. The industry has moved on, so an important part of the project is to perform an industry survey to determine the current and future requirements of the micro BGA consuming or producing industry. We needed to ascertain if the DOW, the document of work, or EC project speak for the scope of the project, is still current, and we needed to know whether we needed to extend the DOW, the project scope, to meet the European industry requirements for now and for the future. An industry survey was then conducted to gather the opinions of the BGA and the electronics industry. The distribution was primarily through the small to medium-sized member associations, the SMEAGs, the beneficiaries of this research, directly to their members. The research was gathered through focus groups where industry specialists got together to discuss in open forums different questions in terms of the current requirements and the future directions. Individual interviews with key players in the industry, and an electronic survey that was distributed to a very large number of members and interested parties by the SMEAGs. Data was analysed, and the DOW was then re-evaluated. What I'll run through now are some of the findings, and then how we have amended the DOW and the scope of the project in view of the findings. The first thing that we'd like to talk about is the solder alloy requirements. In many ways, it ratified the technical objectives through the market survey. We had originally been focusing on SAC 305, and you can see here the breakdown of the tin, silver and copper on my screen. And from the survey, almost 80% of the respondents used this as their preferred lead-free solder. It's probably important to state at this stage that one of the objectives of the project has a very environmental slant, and one of the SMEAGs is the Portuguese environmental agency, APAMETA, and part of the dissemination will be supporting a environmentally stable and lower impact way of producing micro-BGAs. So our primary focus is on lead-free solders. However, somewhat over 40% of the respondents still said that they use lead-containing solders, and the primary was tin 63, SN 63, which more than 40% of the respondents said they are still using, and will form a part of the scope of the project. This next figure shows the distribution of the solder alloys. This one here is for low melting points, and as you can see, roughly 80% of the respondents' key concern is with SAC 305. Probably not just about half that many of respondents. Following that result, were still interested in lead-containing solders, but the large number of other solders we looked at had very little market response. So it very much ratified the original DOW focus on SAC 305. The next thing I'd like to look at is the micro BGA's overall requirements, and you can see here on the screen the main requirements are the solder alloy type, which we've just covered, the sphere size in terms of diameter and tolerance, and the yield that the manufacturing can produce. Will require imaging of solder spheres and analysis, and some complicated man-machine interface, self-correcting algorithm software systems that we'll need to create as part of the project. looking at a table that shows the preferred sphere diameter and tolerance of solder balls, we investigated, we asked in the survey the tolerance that would be acceptable for spheres of diameters between 300 microns to 200 microns, between 200 microns and 100 micron, and sub 100 micron down to 50 microns. You can see in this table here that for the solder ball diameters of greater than 100 micron, a tolerance of 5 microns was acceptable. Fairly logically, as the tolerance, as the diameter size moved to sub 100, a tolerance of 5% became a significant component of the diameter, and the tolerance moved to plus or minus 2 microns for the target ball grid array solder ball that we're looking at producing. When we looked at the breakdown of the industry in terms of the CPK, the Process Capability Index, the consistency of the yield, then we found a fairly even distribution. Most people comfortable with CPKs of 2 to 3 standard deviations around the norm, or most of their solder balls falling within 3 standard deviations around the norm. But there was still a significant group of micro BGA consumers who needed a much higher degree of consistency in the solder balls that they were consuming. The revised project specification, based on the survey, came up with about a dozen things that we needed to look at. The first thing was the original diameter of solder sphere that we were aiming at, probably 2 years ago when the project was first proposed, was 100 microns. Our new target is 75 microns, and we're hoping to get down to 50 microns. As you can imagine, this is a fairly challenging target. The throughput has remained the same. It's 500 million, 500 million. This is calculated on a target of around 15,000 to 18,000 spheres produced per second, with an 8-hour production period. The DOW specification was plus or minus 2 microns. We have a current target, initial target of 5 microns, as there isn't quite the consistency required across the entire industry, but we are aiming at getting down to that the original target of a 2 micron tolerance for the 50 micron and 75 micron solder ball diameters. The solder type, the core solder type of SAC 305 has remained consistent, though we want to also look at tin 63 for consumers still using lead-containing solder, and we'll also be looking at some higher temperature solders, as respondents from the automotive industries, respondents from the aerospace industry, and from the chemical manufacturing industries stated that they required solders with higher melting temperatures. for some of their electronic systems. The Process Capability Index, the CPK, the original DAW specification was for greater than 1.33. The initial target has been relaxed to 0.66, but again the desirable objective for the consumers of BGAs and microsoldables with higher and more consistent yields will be 1.33. The BGA inspection system, we originally proposed CCD imaging, and that will certainly be the primary area, though we'll also be investigating some innovative uses of radiography within the project. We hope to be able to provide some additional information using radiography. The BGA appearance was something that wasn't originally specified, but as a result of from a lot of, in many ways, the Smart Group member associations, the members of the Smart Group associations, we had a lot of input that the surface of the BGA needed to be free of oxidization, free of scratches and free of cracks. So that's one of the new targets. One of the targets that was very strongly probably rejected was the initial concept was that we may coat the solder spheres with some sort of protection from oxidization. The feedback, particularly from the focus groups, was that this would be not only unnecessary but probably a hindrance to production. So the Micro BGA project has dropped the requirement for a coating. Pricing. One of the core objectives is to have a financially viable business model, and the sphere pricing per 1,000 spheres in euros was something that was not considered in the original DAW. The survey has determined that we can, if we can achieve a 2.5 euro per 1,000 spheres, the business would be viable in terms of having a production mechanism within Europe that means that the European community is not reliant outside its own borders for its Micro BGA supply chain. However, to not only maintain a business within Europe, but to be competitive and drive this technology back out into the rest of the world, into China, Japan, and the United States, the desirable outcome from the production process would be a 30 to 40 euro cent price per 1,000 spheres. That's the background on what the project is looking to achieve. If I can now I'll now move on to some slides that talk about routes to realising the project objectives. Now I'll just wait for a second while your screens refresh. Here we go. I believe you can all probably now see the solder sphere manufacture diagram that that I'm seeing on my screen. If there's any delay in presenting this, then please flag it to Bob, and he'll flash a little message on my screen. But hopefully you're all getting what I'm getting right now, which is the solder sphere manufacture. The routes to realising the project objectives. What you're seeing in this diagram here is a fairly much state-of-the-art solder ball manufacture system. What there is a solder alloy feed system. So this is usually a tank, although it could be a wire feed system as part of it, which is providing the solder into a jetting tank. The jetting tank would be dispensing the solder balls as a continuous stream of balls. This continuous stream of balls will be imaged using strobe and some sort of lighting technique by a high-speed CCD. The ball size, shape, consistency, numbers will be analysed using very innovative FPGA hardware-based assessment. This will be compared to the CPK that we're requiring to achieve, and a feedback loop will be sent to the production system. After ejection, you can see here an electric plate. The solder balls will have a charge imparted to them to prevent conjoining, and we'll be able to, by placing a charge and deflecting the solder balls depending on their size, we are aiming at being able to perform an initial filtering after making sure the balls are separated. These will then go into catchment area, and another innovative part of the project will be an attempt to directly place spheres onto a substrate. This will all be being performed in a nitrogen-rich atmosphere, which is oxygen-free, to prevent oxidation of the surfaces. Running through our methodology, what we're looking at doing is producing a solder alloy feed system with either liquid alloy or a solder wire with a provision for controlled melting and feed through. We then want to break up the solder stream into a jet of individual balls of consistent size using an ultrasonic frequency transducer. We will be investigating both magnetostrictive and piezoelectric transducers. We'll be then imaging the balls with high-speed, high-resolution CCD camera, and then in conjunction with a lighting source, a laser, LED, strobe, or unstrobe type lighting. We'll be then using a image analysis to analyze the consistency, the size, the sphericity of the solder balls being produced. Initially that was considering an in-house development, or actually investigating if commercial software were available. The project is too challenging for commercial software, and this is something that we'll be producing within the project, an in-house developed software, which will be reconstructing 2 or 3D dimension images and extracting the parameters of the solder balls being produced. This is a critical part of the of ensuring that the system can provide a real-time control. The images that are analysed from the falling balls will be compared against the tolerance, and a real-time control will feed back instructions on various parameters to the solder dispenser within microsecond timescales. As mentioned earlier, the target rate for ball production is around 15 balls, 18,000 balls per second. So the man-machine integration with the BGA system will be for the initial setting up of the conditions. The real-time control will need to be responding to very small fluctuations and providing very quick new parameters to the solder production tank. The solder balls will be separated so they don't conjoin using the inducing it by an induction of an electric field, an electric charge on the balls, and the oxidation will be prevented by providing a nitrogen-controlled environment to remove the oxygen from it. And so the surface of the balls will be nice and smooth and shiny. The ball filtering system, inevitably there will be some balls that aren't suitable, balls that do not fall within the specification. They need to be separated. We're looking at a couple of technologies such as mass spectrometry and a couple of low technology solutions like micro-sieving. And finally, the placement of solder balls directly onto PCBs will allow a system of micro solder balls to be integrated with the packaging placement onto PCBs. These, as you can imagine, are quite a challenging series of specifications that we've broken down our technical objectives over the 3 years of the project into some milestones. The first year, we've already completed the system specifications and requirements. During this year, we'll be developing techniques and a prototype for a solder alloy feed system. We'll also be developing a technique and a prototype for jetting out consistently sized micro solder balls, which are separated from each other and allowed to form into highly spherical, very consistent shapes. We'll be developing through the first year of the project and extending into the second year of the project these techniques for observing and measuring the solder balls, and again extending through from the first year of the project into the second year of the project. We'll be developing techniques and prototypes for separating the balls, and that will leave us ready for the start of the second year to be able to integrate these different systems into a integrated solder feed, jetting, separating the solder balls, measuring the solder balls, and ideally in preparation for placement into one integrated lab system. This lab system, the ball imaging data will be then taken into a control system which will compare the produced balls parameters against the target parameters and be providing near instantaneous feedback to the production tank. And in the second year, we'll also be developing the ball filtering system. So at the end of the second year, we are aiming at having a system that is ready for a production or a prototype that can be tested out in the field. So the third year of the project will be extensive field trials of the system, taking feedback from on the system, doing modifications to the system, particularly in the feedback in the instantaneous feedback loops area, and the training of the genetic algorithms that will be controlling this process. The field trials will then lead to of the soldable manufacture system will then feed into the development of a prototype for ball placement, and then we're looking for industry partners to be testing the produced soldables and micro soldables and micro PGAs to demonstrate a production environment. This will go through several phases. The first will be a testing phase where we'll be using test packages to establish connectivity and resilience. But after that, then we'll be using the micro soldables produced to actually use to be used in real electronic components and electronic devices to prove the concept of that the soldables are actually usable in a production environment. What I'd like to go into next is to run through some of the existing processes, and give you a quick historical view of the different techniques that have been used through time, and look at some of the issues that are facing with them. What we have here on the far left-hand side of the screen is the original solder system back in 1993, the solder ball production system, back in 1993, produced by MIT in the States. A couple of the key features you can see is this upside down dark T is your transducer, which is producing a pulse, almost pushing the solder balls out through multiple nozzles. It's a high production system that was designed to make a large number of micro solder balls. In the next system here, you can see something from 2000. Many of the same concepts are being retained. There's your piezoelectric actuator, producing the consistent balls that are coming out of the outlet. You can see in this system here, the solder metal as it comes out is having a charge applied to it, so that the charges, so the solder balls will repel each other and not bump into each other in the molten state, or even after solidifying and either join together to produce defects or to possibly damage each other. The next was an innovative system. This is again from 2000, and an innovative system where you can see a piezoelectric sleeve. So instead of an actuator which mechanically pushed out the solder balls, this one here squeezed them out one by one. The advantage of this is that you can place them almost in a inkjet type technique. You can place the solder balls directly onto the substrate, so incorporating the ball production with the actual placement of the ball. So you can sort of see in those 7 years quite a bit of innovation. A lot of the core concepts have been retained, but many of there are new innovations in the technique. In the next slide, I want to jump forward in time and look at a system from 2005 that did not use any actuator. The system itself was just governed by pressure, where the internal pressure within the molten solder tank was balanced against the surface tension that stops the solder ejecting, and the process control was solely by the pressure of the nitrogen within the tank. This is again another innovative technique where the use of nitrogen, the nitrogen control, fed through the entire system, down through the piezoelectric element, and the nitrogen environment flushed out onto the substrate as well. Here again in 2010, in 2010 we can see a system that again has many of the same features that the original MIT system did, in that there is a change in pressure, generates the push conditions, the vibratory shaft, make sure the balls come out in a consistent format. And finally, this system here in colour in the bottom to show I suppose the current state of the art for many systems is your core solder ball production system using a nitrogen environment to maintain pressure and transducers to maintain consistency of solder balls. But you can see here a CCD camera, some sort of imaging, some sort of lighting system, and then feedback into control systems, so that the entire process is becoming far more automated. The challenge that you'd face with humans controlling a system like this is that the fluctuations happen on a very rapid basis, and the production speed that we're looking at of 15,000 to 18,000 balls per second mean that the rate that we as humble humans can respond to the fluctuations in the system are not fast enough, and we need to, this is why the innovative feedback systems that will be created are very important. Now, one of the challenges with all of these systems is that, as you can see, they have all been patented. All these systems, all the production systems that are currently available, whether in Europe or outside of Europe, are systems that the intellectual property is the property of the organisation that is producing them. One of the core objectives of the uBGA project is to ratify a lot of the research that has been done at different times, to find a technique that produces solder balls in a consistent and industry acceptable way, to go beyond that, to miniaturize those balls, and then to hand those findings over to the beneficiaries of the project, which are the SME, the small to medium-sized enterprise member associations that are the beneficiaries of this project. And breaking news, what I'd like to show you here is some breaking news on the 100 micron spheres that we've produced within the first year of the project. As you can imagine, it's quite a happy moment for us. These were just produced this week, almost on order for the Smart Group webinar. This is very encouraging. As you can see, there's a long way to go. You can probably see some conjoined spheres in this area here that are still coming out and not separating. You can see a couple of spheres here that are conjoining during the falling process. But overall, we can see a very consistent sphere size. You can see some challenges in terms of giving the ball sufficient time to be able to fall, and the surface tension to be able to correct the shape and make them nicely, consistently spherical. But overall, we're very, very pleased with this result. So the next question is, where do we go from here? What are the future industry benefits? I mean, the benefits, the core benefits that the EU see the project providing is in terms of micro-BGA manufacture, is to initially be competitive with and independent from Chinese, Japanese, and US manufacturers. We're also hoping that that European facilities using local funding, which could be available as a percentage of capital expenditure or salary costs, can also be set up. And we've had some very positive feedback from some of the SME AGs. One of our SME AGs is SEPVE, the Northern Greek Association of IT companies. They've already identified some members that are considering becoming production facilities for us. The micro-BGAs, the miniaturization of economically viable, consistently produced BGAs, will lead to new application areas in electronics, medical areas, and many other areas. The work that the project will be doing, the very innovative work in terms of new vision systems, the fast imaging systems using neural networks, by one of the partners, IKH, a Greek research organization, will be, we hope, applicable to not just the production of micro-BGAs and the process control of this specific area, but we imagine this will be a very innovative area that will lead to exploitation in many other areas. As is often the way when a technology has been innovated or improved, many of the ways that are possible to use it are only discovered once it's actually been there. So there are many other innovative technological areas that we hope this miniaturization of the connection between packages and the PCB, the PC board, will lead to. Here's a quick overview of some of the members of the members of the consortium. As you can, Smart Group Ireland and Smart Group UK, who are our hosts for this webinar, are one of the SME organisations. SEMI, the semiconductor manufacturing industry organisation in France and now through Europe, is one of the SME AGs. We have two Greek IT member associations, SEPVE, who I mentioned earlier, who have already identified some potential members for being manufacturing facilities, and SEPI, which is the Federation of Greek ICT enterprises. We have Apamata, I mentioned earlier also, is a SME AG in the Environmental Agency, a Portuguese based in Lisbon. We have a group of small to medium-sized enterprise companies as well. We've got Semicon and Avis from Poland, representing control process manufacturers with Avis, and Semicon are reflow and placement specialists. CIT is a specialist in radiography and will be assisting in terms of the imaging and innovative radiographic techniques. And Kingston Computer Consultancy will be working primarily on the ultrasonic work as well as the production work of the solder balls. And IKH, I Know How, the Greek research partner, will be working with the innovative imaging and feedback techniques. At this moment, I'd like to thank you all for your participation. Before I hand back to Bob, I'd like to quickly show you our website. It was on the last slide, but you can see here this is the website that the findings will be disseminated on. There will be blogs and forums, and it'll be a major route for dissemination. So please add this to your favourites. And on that note, it really just is left for me to thank Bob and Tony from Smart Group UK, to thank Philip from Smart Group Ireland for their support in the project to date, to thank all the partners and you the audience for attending here, and hand back to Bob to have any questions.
Thank you, SP. Okay, I would now like to take the opportunity of asking if you have any questions relating to the presentation that has been presented. Now, there are two ways of asking any questions. You can either click on the raise hand tool, and that indicates to me you have a question to ask, and what I will do is unmute your microphone, allow you to ask the question, and if you're in a room environment, a room session, what I'll do is remute your microphone directly after you've asked the question, allowing the question to be asked. Alternatively, what you can do is type your question into the control panel, and I'll read out the question, allowing our two presenters who are around to answer these questions for you. So two options: either click on the raise hand tool and I'll come to you, or alternatively, if you'd like to click into the control panel and type your question in, we'll be able to ask that. Before I go to answer the questions, just to give you a couple of moments to either write your questions or click on the control panel, I'll just briefly mention other events that Smart Group have coming up in the not too distant future. And here it's available from the Smart Group website, but here listed, and will be listed on the slides, you'll be able to see details of different events that are coming up both in England, Scotland, and of course in Ireland. So let's check out the questions. First of all, we've got a couple of typed questions in, which is kind of useful. Right, we have two questions from somebody who knows a lot about solder ball production, so it's probably the difficult question. I'll leave those two to the last minute. And I know Roger knows who I'm referring to. Anyway, first question is, are the solder balls for BGAs manufactured similar to ones for solder paste manufacture? I believe there is a difference in the tolerance. So the question is, are solder balls for BGA manufactured in a similar method to ones for solder paste manufacture? I believe there is a difference in the tolerances involved. I don't know if SP or if Ravin wants to take that. I'm going to unmute Ravin's microphone as well, so you're both available. So please quiet in the offices.
Hi, Bob. Not 100% sure about this question. I might need to come back to you, but a couple of things come to mind. One is the tolerance. The other one is the CPK. I mean, here with the balls, we are trying to make the balls consistent from each other with a high or very low rejection rate. So I feel that that might not be applicable to solder paste.
Okay, Rabin, thank you very much. Just if I mute your microphone, because we're getting echo between yourself and SP, so if I just mute your microphone for a moment, and perhaps if there's other questions that you answer as opposed to SP, you just use the same microphone if you can do that, because there's a lot of echo. Okay, next question. This is again a question which has been written in. Has a multiple hole dispenser been considered? This would reduce the frequency needed for the vibration system. And as I said, the gentleman asking the question does know quite a lot about solder sphere manufacture. SP.
I'll take that one. Yes. Well, that is a good question, and that was the if we think back to the slides that I showed, the original MIT system was a multiple hole system. We will during the project look at innovating the single hole solution, but in terms of maintaining a high CPK. We feel it's easier to control a single hole system to the level of 1.3 than to be trying to manage 3 separate holes. The other challenge that we're facing on the project is with the imaging system. The processing of the data is a fairly enormous task. And establishing the rate of response that we're going to need in terms of microseconds during a 18,000 ball per second production means that we want to focus initially on a single stream of microballs rather than have a larger number of outputs. I hope that answers the question.
No, I think it's a very good answer. Next question. How do you expect to avoid existent patents by the methodology that you're using?
Yes, good question. This is one of the core questions in terms of the intellectual property. There is a large number of patents out there. They need to be sufficiently different from the previous ones. Patent law is happily not my core area, but the innovations, the core thing, the key thing you're looking for in a patent and avoiding other people's patents is to be able to do something which may be similar, and as you can see from a lot of the diagrams we put up, there are very core concepts. There is a core concept of using nitrogen pressure within a solder tank. There's a core concept of using, generally speaking, some sort of transducer to maintain consistency. There are core concepts of ejecting into nitrogen. However, what we're looking at doing is innovating in terms of a number of areas. We expect that the specifics of the system, producing solder balls smaller than 100 microns, are going to require some changes in terms of the microphysics. So we're expecting the design to be significantly different from existing patents, so that it is actually patentable. And to have new features such as the imaging, which is existing in some systems but not with the feedback loops, to also be sufficiently innovative and distinctive, so that we, one, avoid other people's patents, and two, produce intellectual property that is protectable for the member associations of the SMEAGs that are involved.
Okay. Thank you very much for that answer. It would be very interesting if Roger wants to come back with a supplementary question or also come back with any issues he sees with patent issues based on what you've said. We have one delegate who's raised their hands previously during the presentation, and I'm just going to check and see if Anna still wants to ask a specific question. Anna, I'm going to unmute your microphone if you'd like to ask the question to SP, and then I'll re-mute your microphone. So I'm unmuting your microphone now to allow you to ask the question. Anna, please go ahead with your question. Okay. I'm going to cancel that raise hand as Anna doesn't seem to be able to ask that question at the moment. So if you still want to ask a question, Anna, please raise your hand again. I've cancelled that. Another question is, where do you see Europe competing sensibly on sphere manufacture? Obviously, a lot of other companies have had a lot of expertise in making spheres over the years. So where do you see a key area for Europe to influence? Is it on cost, quality, or manufacturability?
This is a challenging question to Europe on on many issues at this moment. Competing with a very low labour cost or a head start in the manufacture of a technology always provides a difficult and challenging environment to enter a market or to regain a market. The two key areas that we feel this project would be suitable, allows us to compete effectively in the market in the feedback loops that the feedback loops that IKH will be producing for the project, and also the CPK, the consistency of the yield. Now, that then I suppose begs your question from your listener, Bob, is what sort of electronic devices will it be used in? Part of the project is identifying the initial areas. So we do have partners that have already identified that they would be interested in using our soldables in the production of their electronic devices. And part of the reason for the dissemination that Smart Group, CEPI, SEMI, and Appamata, the SME AGs will be doing for us, is to help us identify other market opportunities.
Okay.
So, in a way, I'd like to throw that question back to the questioner, where they would see, and what I'd like to ask the entire audience is where that is actually where they see our markets being, how they can see Europe protect our part of the market, protect our supply chain, and compete with the rest of the world.
Okay, well you've posed the question. Let's see if somebody comes back to you. But in the meantime, there's a question just come in from Steve, and this is a question from an industrial partner. What method will be what method will be evaluated regarding placement with a view to the microsphere size and reducing pitch requirements? So basically, the question relates to the solder spheres after production. What methodology will be used to assemble those to the BGA substrates to make the parts to assemble to the printed circuit boards?
Okay, so that's a challenging question for us, and that's one of the things we're currently in the process of looking at. we've got a range of different technologies that we're looking at in terms of placement after the balls have been manufactured, and ideally during the project placement as the balls are being generated. What we're looking at are the normal sort of placement techniques of sieving and placing them into grids as are normally done in industry right now. Ideally, where we'd like to head is similar to an inkjet placement. Is the ability to be generating solder balls in a very miniaturized melt environment, to be placing them directly onto the IC in the package. That would allow not only primary manufacture to be facilitated, but also to reworking of defected items to be included in the exploitation plan.
Okay, so obviously looking at all potential options for the use of the spheres.
We are indeed.
Okay, just take a couple of moments of clear space. If you have any other questions, if any of the delegates would like to ask any other questions, if they'd either like to raise their hands on the control panel and I can unmute the microphone, allow you to ask the question directly, or alternatively, as you've been doing so far, type a question directly into the control panel. Okay, next question. Notice that you included tin, copper, nickel as one of the alloys in the survey. Is there intention to try different solder alloys over and above the selected lead-free and tin-lead alloy?
Ideally, there's a couple of different areas we've thought about in terms of the different solders. We would like to look at indium solders. We would like to look at high temperature solders. The primary focus of the work is going to be SAC 305. It depends very much on the progress of the project. Obviously, initially, with any project, you need to achieve the core objectives of the project, and for us, that is SAC 305. The secondary objective would be then, tin 63, and from that, then there are a range of other solder types that we find that we're pretty excited by.
Okay. So final opportunity to ask any other questions. If you'd like to either type the question directly into your pane on your screen, or alternatively if you'd like to click your raise hand tool, we can ask the question direct. So I'm just going to leave again a little bit of space, i.e. dead space, and just see if there's any more question. As soon as you say it, somebody else comes online. Hi, I've actually done any market surveys on current and future market price. Hi, have you... sorry, I read the question incorrectly. I apologize. Have you actually done any market surveys on current and future market prices? I think that's an easy one for you to answer, SP?
Yes. Thank you, Bob. Certainly, Smart Grid were very, very helpful in the survey. That the first part of the project was a survey to determine what the current prices are, what historic prices are, and what we expect prices to be competitive. So yes, we have.
Would you like to elaborate?
There was a slide, and what we are ultimately aiming for is a 30-40 euro cent per thousand pricing for SAC 305.
Okay, can I just ask, is the survey results now on the website that delegates can go to?
I don't believe it is at this stage. It has been submitted as a deliverable to the EC, and we are still waiting for the EC's final acceptance of that. once the EC's accepted that, it'll certainly be a document which we will disseminate via the website. What we could do is, if any of the audience are actually would like a copy of the document, then if they contacted you, we could look at getting any information they need out to them.
Okay, so jumping the gun slightly, especially for smart group engineers. Okay, okay. So again, each individual that completes a survey at the end of the webinar will receive a copy of this presentation. Another question just coming in. The point here in the question is relating to the price actually coming out of the Far East. Now, I believe we actually had some figures that were quoted to us by one of the members of the project when we started the project. Perhaps you'd like to comment on that?
Yes, we did. We looked at prices coming from the Far East. We looked at minimum sizes coming from the Far East. It is competitive. There are some very challenging prices, and there are some very challenging miniaturizations that we're facing. We believe even through the life cycle of the project, what may be like a 50 micron level of competition from the Far East, from Japan and from China, will potentially drop to a 20 micron level of competition. What we're hoping to do with the project is not necessarily compete directly on price, not necessarily to compete directly on miniaturization, to address both those issues, but primarily to bring the know-how of how to produce solder balls into Europe. It's one of the core objectives of the project is the recognition that the Far East is very competitive in terms of price and is very competitive in terms of its production capacity and its level of miniaturization. The challenge that the EU faces is that is an external supply chain, and one of the core objectives of the project is to bring that intellectual property into Europe. Having said that, where we want to compete is in the level of CPK, the level of consistency, and in the optical systems that will allow us to produce very consistent, very high yield BGAs and micro BGAs.
Okay. Okay. Well, I'd like to thank SP for his presentation this afternoon. I know ably supported by Ravin behind the scenes. Behind the scenes. I'd like to thank all the delegates who've participated in this particular event. Again, if you'd like a copy of the presentation, you will get that directly emailed to your email address, provided you fill in or take a couple of moments to fill in the survey form directly at the end of this presentation.